Hello friends, welcome to my lecture on discrete probability distribution. Let us first define a random variable. If we draw 5 bolts from a lot of bolts and measure the diameter, we cannot predict how many bolts will be defective, that is, will not meet the given requirements. Hence, x equal to number of defectives. Let us define x to be number of defectives, then x describes a function which depends on chance. The lifetime of a light bulb to be drawn at random from a lot of bulbs also depends on chance. Thus, roughly speaking, a random variable, also called a stochastic variable or variate, is a function whose values are real numbers and depend on chance. Precisely speaking, a random variable is a function x which is defined on the sample space S of the random experiment and its values are real numbers. Further, if a be any real number and I be any interval, then the set of all outcomes in S for which x assumes the value a has a well defined probability, and the same is true for the set consisting of all outcomes in S for which the values of x are in I. Now, if in a random experiment the event corresponding to a number a occurs, then the corresponding random variable x is set to assume the value a and the probability of the event is denoted by Px equal to a. Okay. Similarly, the probability of the event x assumes any value in the interval a less than x less than b is denoted by Pa less than x less than b. The probability of the event x less than or equal to c, that is x assumes any value smaller than c or equal to c, is denoted by Px less than or equal to c, and the probability of the event x greater than c, that is x assumes any value greater than c, is denoted by Px greater than c. The event x less than or equal to c and x greater than c are mutually exclusive because their intersection is phi. Hence, Px less than or equal to c plus Px greater than c is equal to P minus infinity less than x less than infinity. We know that if a and b are two mutually exclusive events, then by the axiomatic definition of probability, Pa union b equal to Pa plus Pb. So, here if a denotes the event x less than or equal to c and b denotes the event x greater than c, then Pa plus Pb is equal to Pa union b, and a union b is the real axis, that is minus infinity to infinity. Now, by axiom 2, the axiom 2 of the definition of probability says that probability of S, the sample space S, is equal to 1. So, probability of minus infinity less than x less than infinity is equal to 1, and therefore, probability that x is greater than c is equal to 1 minus probability of x less than or equal to c from this equation. Now, for example, suppose x is the number that turns up in rolling a fair die. Suppose we roll a fair die, then the probability of getting any number, say 1, 2, 3, 4, 5, 6 is equal to 1 by 6. Okay. So, probability of x equal to 1 is 1 by 6, probability of x equal to 2 is also 1 by 6, but probability of 1 less than x less than 2. Okay. Now, x takes values 1, 2, 3, 4, 5, 6. So, x is not taking any value in between 1 and 2, and therefore, probability that 1 is less than x less than 2 is 0. Probability that 1 less than or equal to x less than or equal to 2, it includes two integers 1 and 2. Okay. So, probability that 1 is less than or equal to x less than or equal to 2 is probability that x equal to 1 plus probability that x equal to 2, and that is equal to 1 by 6 plus 1 by 6 equal to 2 by 6, and which is equal to 1 by 3. Okay. So, probability that 1 is less than or equal to x less than or equal to 2 is 1 by 3, probability that 0 less than or equal to x less than or equal to 3.2. Now, in this set there are 3 points, 1, 2 and 3. Okay. Each one has probability 1 by 6. So, probability of x equal to 1 plus probability of x equal to 2 plus probability of x equal to 3 is 3 by 6, that is 1 by 2, and then probability x greater than 4. Okay. X greater than 4 means x can take values 5 and 6. So, probability of getting 5 is 1 by 6, probability of getting 6 is 1 by 6. So, probability of x greater than 4 is sum of the two probabilities, that is 1 by 6 plus 1 by 6, which is equal to 2 by 6 and so 1 by 3, and probability that x less than or equal to 0.5. No value of x satisfies x less than or equal to 0.5 because x is taking values 1, 2, 3, 4, 5, 6. So, probability that x less than or equal to 0.5 is 0. Okay. The random variables are either discrete or they are continuous. Okay. Now, let us define a discrete random variable. A random variable and the corresponding distribution are said to be discrete if the number of values for which x has a probability different from 0 is finite or at most countably infinite. Okay. Further, if an interval a less than x less than or equal to b does not contain such a value, then probability that a less than x less than or equal to b is equal to 0. Now, let x1, x2, x3 be the values for which x has a positive probability, and let p1, p2, p3 denote the corresponding probabilities, that is probability of x equal to xi is equal to pi, I takes values 1, 2, 3 and so on. Then we define the probability function of x given by fx. Fx takes the value pj when x takes the value xj. So, fxj is equal to pj for j equal to 1, 2, 3 and so on. So, that means fx is nothing but probability that x takes the value x. Okay. So, fxj is equal to probability that x takes the value xj and j equal to 1, 2, 3 and so on. Okay. So, this is px equal to xj is pj. So, fxj is equal to pj, and when x does not take the value xj, okay, then fx takes the value 0. So, now ps is equal to 1, probability of the sample space S is equal to 1 by axiom 3 of the axiomatic definition of probability. So, we must have sum of the probabilities equal to 1, that is sigma j equal to 1 to infinity fxj is equal to 1. Now, if we know the probability function of a discrete random variable x, okay, then we may compute probability that a less than x less than or equal to b, okay, as follows. Probability that a less than or equal to x, a less than x less than or equal to b is sigma fxj a less than xj less than or equal to b. We will take the sum of the probabilities of the points xj's which lie in the interval a to b, okay, that is sigma pj a less than xj less than or equal to b. Now, for closed, open or infinite interval, we can compute the probability in a similar manner. Here you can take a less than or equal to x less than or equal to b, that is you can take the closed interval a b. Okay. You may also take the open from right on this the side b, that is you can consider a less than or equal to x less than b. Okay. You may also take a equal to minus infinity, b equal to plus infinity. So, you may also consider infinite interval, you may also consider open interval, that is a less than x less than b. We will calculate the probability that a less than x less than b or a less than or equal to x less than or equal to b or probability of minus infinity less than x less than or equal to b in a similar manner, okay, like we have shown here. Okay. We will take the sum of the probabilities at all those points xj's which lie in the given interval. Okay. Now, if x is any random variable, this is true for any random variable, not necessarily discrete. If x is any random variable, not necessarily discrete, then for any real number x, there exists the probability p x less than or equal to x corresponding to x less than or equal to x. Okay. So, we call it as the cumulative distribution function of x and denoted by fx. Okay. P x less than or equal to x is a function of x which is called the distribution function of x or cumulative distribution function of x, and it is denoted by fx. So, fx is equal to p x less than or equal to x. Now, probability of a less than x less than or equal to b can be written as probability of x less than or equal to b minus probability of x less than or equal to a. Okay. So, probability that a less than x less than or equal to b can be expressed in terms of the cumulative distribution function. This gives you fb, okay, using this definition, and this gives you fa, okay, by the same definition. So, the distribution function determines the distribution of x uniquely, okay, and it can be used for computing probabilities. We can compute the probabilities by using the distribution function. You can see FB minus FA gives the probability that A less than X less than or equal to B. Now, if X is a discrete random variable, then from 1, okay, from the definition 1, from this definition, probability that minus infinity less than X less than or equal to X, okay, is equal to sigma xj less than or equal to x. We will take the sum of the probabilities at all those xj's which lie in the interval minus infinity to x, that is xj less than or equal to x. You may also write it as minus infinity less than xj less than or equal to x. Okay. Now, let us consider the experiment of rolling a fair die once. Let x denote the number obtained in rolling the die, then the possible values of x are 1, 2, 3, 4, 5, 6. Hence, the probability function f x takes the value 1 by 6 when x takes the value 1, 2, 3, 4, 5, 6 and f x is equal to 0 otherwise. Now, the graph showing the function f x and the cumulative distribution function f x are as given below. You can see here this is our x axis, okay, and this is the y axis. Okay. So, f x takes the value 1 by 6 when x is equal to 1, 2, 3, 4, 5, 6. Okay. At all the values of x 1, 2, 3, 4, 5, 6, f x takes the value 1 by 6 and it is 0 at all other values of x. Now, this is cumulative distribution function of the function cumulative distribution of the probability function f x. Okay. So, here when x is less than 1, okay, probability that x is less than 1, okay, this is equal to f x is equal to probability that x is less than or equal to x. Okay. So, f x is equal to let me write like this. Okay. So, f x is equal to probability that x less than or equal to x. Okay. Now, when x is equal to 1, when x is equal to 1, okay, f x is equal to p x less than or equal to 1, okay, and p x less than or equal to 1 is 1 by 6. Okay. So, f 1 is equal to 1 by 6. To the left of 1, okay, f x is 0, okay, f x is equal to 0 because the probability f x is equal to 0. Okay. So, at x equal to 1, f 1 is equal to 1 by 6 and then f x, okay, when x takes the value 2, okay, f x equal to p x less than or equal to x gives you 2 by 6. Okay, because x less than or equal to 2 means we will add the probability of x equal to 1 and x equal to 2. So, we get here, okay, we reach here f x is equal to 2 by 6 and then when you take x equal to 3, okay, we reach here, okay, f x is equal to p x less than or equal to 3. So, we get 3 by 6, that is 1 by 2, and when you take x equal to 4, you get f x equal to 4 by 6 and we come here. Okay. Then at 5 we come here 5 by 6 and then 6 we come here and then after that f x becomes equal to 1. Okay. So, if x is greater than 6, okay, greater than or equal to 6, when x is greater than or equal to 6, okay, f x is equal to 1. Okay. Now, in between, okay, if 1 is less than or equal to x less than 2, okay, if 1 is less than or equal to x less than 1 is less than or equal to x less than 2, then probability remains 1, okay, because in this interval 1 to 2 only x equal to 1 lies. So, here 1 to 2 interval, if you take 1 to 2, then the cumulative distribution function remains 1. Okay. So, f x is equal to 1 for the interval 1 less than or equal to x less than 2. Similarly, f x is equal to 2 when 2 is less than or equal to x less than 3, like this. F x is equal to 1 by 6, okay, here it is 2 by 6 and then 3 by 6 when 3 less than or equal to x less than 4, like this. Okay. So, this is how we draw the graph of the cumulative distribution function in the case of rolling a fair die. Now, let us take the experiment of rolling a pair of dice. Okay. We have 2 dice, okay. We roll them together, okay. Then x denote the sum of the numbers appearing on the 2 dice, then the possible values of x are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. The probability function f x has the value. Now, when we will get the number 2, sum of the numbers on the 2 die will be equal to 2 when each one shows 1 on okay. So, that means 1 1, okay. On the die 1 the first number shows die 1, second number shows die 2, okay. So, first number shows on the die 1 we get 1, on the die 2 we get 1, then the sum will be 2 and each one has probability 1 by 6. So, having 1 1, that is sum 2 will turn up, the sum of x will be equal to 2 when we will have 1 1 on both the die, okay. And probability for that is 1 by 6 into 1 by 6, that is 1 by 36. Now, when the sum will be 3, if we have on die 1, we have 1, on die 2 we have 2, on die 1 we have 2, on die 2 we have 1, okay. So, there are 2 possibilities where the sum can be 3, okay. Now, this has probability 1 by 6, this has probability 1 by 6. So, having 1 2 is having probability 1 by 36 and 2 1 will also have probability 1 by 36. So, total probability is 2 by 36 and we get 2 by 36. Now, sum will be 4, sum on the 2 dice will be 4 if we have 1 3, 3 1, okay, 2 2, okay. There are 3 possibilities 1 3, 3 1, 2 2, okay. Each one has probability 1 by 36. So, we have 3 by 36. Similarly, 5 can come when we have 1 4, 4 1, 2 3, 3 2 and then, so we have 4 possibilities, each one has probability 1 by 36. So, we get the probability of having sum 5 as 4 by 36. So, in a similar manner we can compute the probabilities for having x equal to 6, 7, 8, 9, 10, 11. Now, 12 will come when each die shows 6, okay. So, that means 6 6. So, this is 1 by 6, probability of this is having 6 on one die is 1 by 6. So, 1 by 6 into 1 by 6. So, this has probability 1 by 36. So, we have 1 by 36. Now, you can sum these probabilities, okay. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4, this comes out to be 36 by 36 and so sum of probabilities is equal to 1. Now, there are 36 possible outcomes, equally likely outcomes, each of which has the probability 1 by 36. X equal to 2 comes for 1 1 we have discussed, okay, where the first die number refers to the first die, second number to the other die. We have x equal to 3 in the case of 2 outcomes 1 2 and 2 1, okay. So, probability that x is equal to 2 is 2 by 36 and so on. Now, let us look at the graph, okay. So, you can see here this is your 1 by 6, okay. Now, this is 1 2 3 4 5 6 7 8 9 10 11 12, okay. So, we can have sum 2, okay. Sum can come, sum cannot be 1, okay. So, sum can be 2. So, this is 2 3 4 5 6 7 8 9 10 11 and 12, okay. Now, 2 has probability 1 by 36, okay. So, this is 1 by 36, this is 1 by 36, probability that x has value 3 is 2 by 36. So, this is double of this, okay. So, 2 by 36, then this is 3 by 36 at 4, 3 by 36 at 5, 4 by 36, this is 4 by 36, okay. At 6, 5 by 36, so this is 5 by 36 and 7 is 6 by 36, 6 by 36 means 1 by 6, okay. So, you can see this is 1 by 6, okay. At 7 the probability is 6 by 36, that is 1 by 6, okay. So, and then at 8 the probability is 5 by 36, same as the probability at 6, okay. So, you have the same height here at 8, okay. Then 9 has the probability 4 by 36, 4 by 36 means the probability for having the sum 5, okay. And then 10 has probability 3 by 36, So, it is of the same height as the height at 4, and then 10, 11, 11 has 2 by 36. So, it has the same height as the height at 3, okay. And then the probability that x is equal to sum is equal to 12 has the same height as the height at x equal to 2, okay. So, this is the graph of the probability distribution of x, where x denote the sum of the numbers on the 2 dice when we roll them, okay. Now, this is cumulative distribution function. We can see here that this is 2, 3, 4, 5, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay. So, probability that f x equal to probability that x is less than or equal to x, okay. So, if you take x to be 2, okay, let x be 2, okay. So, then this is probability that x is less than or equal to 2 is x equal to the probability of having x equal to 2, x equal to 2 means 1 1, that is 1 by 36, okay. So, you can see this is 1 by 36, then at x equal to 3, we have 2 by 36, okay. So, x equal to 3 has probability 2 by 36, x equal to 1 has probability 1 by 36. So, 1 by 36 plus 2 by 36, we have to add the probability at x equal to 1 by 6. This is equal to probability that x equal to 1 plus probability that x equal to 2. So, this is equal to 1 by 36 plus 2 by 36. So, we get 3 by 36, okay. So, this is 3 by 36, this one is 3 by 36, okay. And then if you find the f x for x equal to 4, okay. So, f x, this should be f x, okay, f x where x is 4, okay, p x less than or equal to 4, okay. Let x be 4. So, then this is probability that x is equal to 1, x equal to 2, x equal to 3, x equal to 2, not x equal to 1. Two, 3 and 4. And here we have to write 2 and 3, okay, 2 and 3. So, this will be 1 by 36, 2 by 36, and 4 comes when we take 1 3, 3 1 and 2 2, okay. So, we get 3 by 36. So, this comes to be equal to 6 by 36, okay, 6 by 36, and when you take x equal to 5, okay, here, okay, x equal to 5, you will see it comes out to be 10 by 36. So, we have f x then equal to p x less than or equal to 5, and we get p x equal to 2, p x equal to 3, x equal to 4, x equal to 5, okay, which is equal to 1 by 36, 2 by 36, 3 by 36. So, probability that x equal to 2 plus probability that x equal to 3 plus probability of x equal to 4 is 6 by 36. We have to add the probability of x equal to 5, and x equal to 5 comes when we have 1 4, 4 1, 2 3, 3 2, okay. That means we have 4 cases. So, 4 by 36, okay. So, 6 by 36 plus 4 by 36. So, we get 10 by 36. So, you can see here when x is equal to 5, it is 10 by 36, okay. And similarly, we can calculate, and when x is 12, okay, when x is 12, the sum of the probabilities becomes equal to 1. So, when x is equal to 12, okay, f x is equal to p x less than or equal to x will be equal to 1, okay. And then when x is greater than 12, okay. So, thus when x is greater than or equal to 12, f x is equal to 1, okay. So, this is like this, okay. So, this is the cumulative distribution function of f x. Now, the mean of a discrete random variable. When you have a discrete random variable, the mean of the discrete random variable is given by sigma over j x j f x j, where x j's are the values taken by the random variable x, okay. We multiply x j by the corresponding probabilities and take the sum over j. The variance is given by variance of x equal to sigma square, which is sigma over j x j minus mu whole square into f x j. That is, we multiply the deviation of x j's from the mean, square it and then multiply by the probabilities of corresponding probabilities and take the sum over j. Now, this expression comes out to be expectation of x square minus expectation of x whole square. We can easily see this. Let us write sigma over j x j minus mu whole square into f x j as equal to sigma over j x j square minus 2 mu x j plus mu square into f x j. Then this will be sigma over j x j square into f x j minus 2 mu is a constant, sigma over j x j into f x j plus mu square sigma f x j sum over j, okay. Now, this is equal to sigma over j x j square f x j is expectation of x square, okay. The first term, sum is f e x square minus 2 mu sigma over j x j f x j from here, okay, is mu, okay, it is mu. So, minus 2 mu square and then plus mu square sigma over j f x j equal to 1, sum of the probabilities is equal to 1. So, this is E x square minus mu square, okay, which is E x square minus E x whole square, okay. So, we have this result, okay. So, variation of x can be expressed in terms of the expectation, it is expectation of x square minus expectation of x whole square. Now, let us consider this problem. Let x denote the discrete random variable which denotes the minimum of the two numbers that appears in a single throw of a pair of fair dice, okay. Then determine the discrete probability distribution of x, okay. So, now if the minimum of the numbers on both the die is 1, okay, this can happen how many in how many cases are there where minimum will be 1, 1 1, okay, 1 2, 1 3, 1 4, 1 5, 1 6, okay, and then we have 6 1, 5 1, 4 1, 3 1, 2 1, okay, 1 1 we have already taken. So, there are 11 cases 1 2 3 4 5 6 7 8 9 10 11. Well, each one has a probability 1 by 36. So, we have 11 by 36 probability, okay. Similarly, if you want the minimum on the of the two numbers to be 2, then the cases are 1 2, 2 1, 2 3, 3 2, 2 4, 4 2, 2 5, 5 2, 2 6, 6 2 and 2 2, okay. So, we have one pair here, one pair here, one pair here, one pair here. No, this will not come because the minimum we want to be 2, okay. So, this will not come, minimum we want to be 2, their minimum will be 1, okay. So, here, so we have but 2 cases, here 2 cases, here 2, here 2. Okay. So, 8 plus 1 9. So, we have 9 by 36. So, similarly, if we want the minimum to be 3, there will be 7 cases. Okay. So, each one will have probability 1 by 36. So, we will have 7 by 36. Okay. So, this is the probability distribution of the discrete random variable, which is the minimum of the two numbers that appears in a single throw of a pair of fair dice. Now, let us take the example for a stack of rupees 44 is to be won between two players A and B, whoever gets 6 in a throw of die alternately. Now, determine their respective expectations if A starts the game. Okay. So, let us find the probability that A wins. So, probability that A wins. Okay. So, if he gets 6 in the first throw, he will win. Okay. So, probability of A wins will be 1 by 6. Okay. Suppose he does not get 6 in the first throw, then what will happen? The B will get a chance. Okay. So, then B should not win because we want A to win. Okay. So, B should not win. So, in the next case what will happen? 5 by 6. Okay. Because if in the first throw he does not get 1 by 6, that means that the probability will be 5 by 6, and then B will get a chance. B should also not get 1 by 6. So, the probability will be 5 by 6, and then A gets the chance. A should, if we want A to win now, then the probability will be 1 by 6 because he should throw 6. Now, if he does not throw 6, then again the probability will be 5 by 6. It will go to the player B again. So, 5 by 6 into 5 by 6 into 5 by 6, okay, and then 5 by 6 into 1 by 6. So, he does not get, in the first chance he does not get 6, the probability will be 5 by 6, then B also does not get 1 by 6, the probability 5 by 6, then A gets the chance, the probability will be 1 by 6 if he wins. Okay. If he does not win, then 5 by 6 plus 5 into 5 by 6 into 5 by 6, then B will get a chance. B should not throw 6. Okay. So, 5 by 6, then A will win if he throws 6. So, that will be probability 1 by 6. So, and so on. Okay. So, now this is a geometric progression, and the sum of this series is A upon 1 minus R. So, 1 by 6 minus 5 by 6 whole square. So, this is 1 by 6 divided by 1 minus 25 by 36, and this comes out to be 1 by 6 into 36 by 11. So, we get 6 by 11. Okay. So, determine their respective expectations. So, expectation of A will be equal to probability that A wins. So, that is 6 by 11 into the amount, that is 44. So, rupees 24. Okay. So, determine the expectation of A, okay, will be 24. Similarly, probability that B wins, because A starts the game. Okay. So, B will win because if A does not get 1 by 6. So, that means 5 by 6 into, now B will win if we throw 6. So, 5 by 6 into 1 by 6. Now, if B does not throw 1 by 6, then 5 by 6 into 5 by 6, then A should not throw 6. So, 5 by 6, then B will throw 1 by 6, B will throw 6. So, 1 by 6, okay, and then we can similarly have, so 5 by 6 into 5 by 6 into 5 by 6. Now, B does not throw 6. So, 5 by 6, A does not throw 6. So, 5 by 6 into 1 by 6 and so on. Okay. Now, the sum of the series is 5 by 36 divided by 1 minus 5 by 6 whole square. So, this time it is 5 by 36 into 36 divided by 11. Okay. So, we get 5 by 11. Okay. So, EB, the expectation of B will be equal to 5 by 11 divided by into multiplied by 44. So, that means rupees 20. So, expectation of A is 24 rupees, expectation of B is 20 rupees. Now, let us discuss discrete uniform distribution. If x takes finite number of values x1, x2, xn, because we have said when we defined the discrete random variable, we have said that x either takes discrete number of values or countably infinite number of values. Discrete in the case of discrete uniform distribution, x will take only finite number of values. Okay. So, let us say the values are x1, x2, xn, and all of these are equally probable. Okay. Each one has equal probability. So, that means probability of having x equal to x1, x equal to x2, x equal to xn, each one will be 1 by n, because they are all equal, okay, and total probability is 1. Now, x is said to follow a discrete uniform distribution, okay, if x takes the finite number of values, okay, and all these values are equally probable. Okay. Now, let us say for example, x is equal to number shown by a fair die. Okay. When we have a fair die, the number shown by the die, okay, when it is thrown, okay, the numbers are 1, 2, 3, 4, 5, 6, and they are all equally probable. Okay. So, each one has the probability 1 by 6. So, the discrete uniform distribution is generally used if the random variable takes a finite number of values and all these values are supposed to occur equally likely. So, so number shown by a fair die is an example of a uniform discrete distribution. Now, let us consider this problem. If a ticket is drawn from a box containing 10 tickets numbered 1 to 10 inclusive, okay, find the probability that the number is less than 4. Okay. So, when we draw a ticket from the box, okay, all the tickets x takes values 1, 2, 3, 4, 5 and so on up to 10. Okay, x takes the values 1, 2, 3, 4, 5, 6, so on 7 and so on up to 10. Okay, find the probability, and each number, okay, has the same probability, they are all equally probable of being drawn. So, it is the case of a discrete uniform distribution. We want the probability that the number drawn is less than 4. Okay. So, p x less than 4 we want, p x less than 4 means 1, 2, 3. Okay. So, each one has probability 1 by 10. Okay. So, 1 by p x equal to 1 plus p x equal to 2 plus p x equal to 3. So, it could be any number p x equal to 1 or x equal to 2 or x equal to 3, each number has equal probability 1 by 10. So, 1 by 10 plus 1 by 10 plus 1 by 10. When you draw a ticket from the 10 tickets which are numbered from 1 to 10, okay, the probability of drawing a ticket will be having any number say x, where x takes values 1 to 10 will be 1 by 10, even number. Okay. So, probability that x is an even number. Now, even numbers are 2, 4, 6, 8 and 10. So, there are 5 possibilities. Okay. So, 5 by 10, that is 1 by 2. Okay. Prime numbers are 2, 3, 5, 7. Okay. Each one has probability 1 by 10. Okay. So, probability that x is prime, it is equal to 4 by 10 or 2 by 5. Okay. Find the mean and variance of the random variable x. Okay. Now, mean will be equal to expectation of x. So, sigma x p x equal to x, x takes values from 1 to 10. Okay. X takes values from 1 to 10. Now, what we have sigma x equal to 1 to 10 x p x equal to x. Okay. X takes values 1 to 10, each number has probability 1 by 10. So, x into 1 by 10. So, 1 by 10 sigma x equal to 1 to 10, okay, which is 1 by 10 into 10 into 10 plus 1, 11 by 2, because sigma n, okay, is equal to n into n plus 1 by 2. So, this is this 10 will cancel and you get 5 by 5, 5.5. Okay. So, expectation is 5.5. Okay. Then variance is equal to expectation of x square minus expectation of x whole square. Okay. So, expectation of x square let us find. Okay. Let us find expectation of x square. This sigma x square into p x equal to x. Okay. So, x varies from 1 to 10. So, this is sigma x equal to 1 to 10 x square and into 1 by 10. Okay. So, 1 by 10 sigma x square. Okay. X varies from 1 to 10. Now, we know sigma n square. Okay. It is 1 by 6 n into n plus 1 into 2n plus 1. So, let us apply this formula. So, this is 1 by 10, n is 10 here. Okay. So, 10 into 10 plus 1, that is 11, into 20 plus 1, 21. Okay. So, this cancels with this, and what we have here 3 2 okay, 77 by 2. Okay. Now, variance of x is equal to expectation of x square minus expectation of x whole square. So, this is 77 by 2, and Ex came out to be 11 by 2. Okay. So, 11 by 2 whole square. So, this is 154 minus 121. So, we get here 33 by 4. So, that means 8.25. Okay. So, variance comes out to be 8.25. Okay. Now, so with this I would like to end my lecture. Thank you very much for your attention.